Okay, so next up we have Federico Piccarini on Facebook storage. I'm going to look forward to this, and hopefully we'll have time for questions.
Awesome.
Thanks.
So good morning, everyone. My name is Federico. I'm a production engineer at Facebook, and today I want to tell you a little bit about how we run our blob storage services in production. So I'm going to start with a little story. My team historically has taken care of our data warehouse storage, so we sit very close to other data warehouse teams. And one day this guy that works for our data warehouse efficiency team, his name is Josh. He comes to my desk and he shows me this dashboard. So the dashboard that he's showing me is basically the projected space occupation on one of our new clusters. And according to this dashboard, we're going to run out of space on that cluster in about a month. Now, the good news is that we're going to get new racks for that cluster. So that's great. We're going to expand it. However, the bad news is that we're not going to get those new racks in time before we run out of space. And so, as someone that runs a storage service, there are three things that are peculiar to running a storage service that you can do to piss your customers off. The first thing is telling them that you cannot take their writes. They cannot write the data that they really want to write to your clusters. The second thing is when they come to you asking for their data and you're not able to give it to them at the specific moment in time when they need it. And the third one, which is probably the worst of all, is when you lose the data that you've been entrusted to store forever and ever. And that's a very good starter for a hard conversation. So as production engineers or site reliability engineers, we try not to be screamed at. And what I want to do today is basically go through these three aspects of running a storage service. One is storage efficiency, one is data availability, and one is durability. So specifically, we're going to talk about the way that data encoding and dealing with hardware repairs have evolved throughout time at Facebook, and how this evolution has helped us improving our storage efficiency, our data availability, and our data durability. So historically, Facebook has relied on HDFS, the Hadoop file system, for its blob storage needs. And HDFS has served us really well, actually. But a lot of the ideas that we are going to discuss today have shaped the way we have designed our next generation storage system. It is called Warm Storage, and it's already in production, already serving the needs of many of our customers. So let's start with data encodings. Now, the idea here is that every file in our system is represented as an ordered sequence of blocks or chunks. It's equal size pieces of data, essentially. Now, each of these blocks needs to be represented on a server somewhere in some form. And that's essentially what data encoding gives us. So we take a block and we produce the actual sequence of bytes that we need to store. Specifically, we usually store more than one encoded chunk for each block in order to give us some redundancy. And so we also refer to these encoded chunks as replicas sometimes. Now, the easiest way you can go about doing this is essentially taking your original block and replicating it a number of times. That is what we call simple replication. It works, it's great. And specifically at Facebook, for most of our use cases, when we use simple replication, we make 3 copies of each block. Now, I said it's simple, it works great, it gives us some loss tolerance. The bad part here is that if only we use 3 replicas, obviously we can lose up to 2 and we're still able to serve our data. But now we're storing 3 times as much the data that we actually need. So, is there anything we can do better here? Well, obviously this is a rhetorical question, so yes, we can. Reed-Solomon encoding. It is a slightly esoteric way of encoding data. It's called Reed-Solomon encoding, also known as erasure encoding. And it's pretty complex in terms of maths behind it. but the high-level idea is pretty simple. So we take a chunk or we take a block, we split it into n chunks of data, and then we compute k chunks of parity information. So this thing defines a whole family of encodings where the first parameter is the number of data chunks that we generate, and the second parameter, n plus k, is the total number of chunks that we have. So data plus parity. Now, the beautiful property of Reed-Solomon encoding is that we only ever need any n chunks in order to be able to reconstruct our data. And that's pretty great because it means that we can lose up to k chunks and we're still good. So if we go back to the same table that we were looking at before, if we have Reed-Solomon16, we have already a better loss tolerance than we have with 3 replicas at about half of the replication overhead. Same with 1014, another common encoding. Now we can lose up to 4 chunks. We're still able to serve our data, and we incur a 1.4x replication overhead. Another encoding that we use for a lot of use cases at Facebook is 918. This time we have a 2x replication overhead, but we can lose up to 9 chunks, which is pretty awesome. There is no free lunch, however, isn't there? So here, what we're doing is basically trading CPU for storage efficiency. Because when we need to compute those parity blocks, what we're doing is actually running some pretty CPU-intensive matrix operations. And the other thing is that we actually incur a read amplification effect on repairs. So if we go back to the same table that we were looking at before, and we add a column for read repair amplification, we see that for the single replication or the simple replication strategies, every time we need to reconstruct one of our missing chunks, essentially what we need to do is going back to one of the existing chunks and copying it somewhere else. So we read it once and we're good. Now, the problem with Reed-Solomon encoding is that that's not enough anymore. So we lose 1 chunk, but now we need to read n. So with Reed-Solomon16, we lose 1 chunk, and now we need to read 6. 1014, we need to read 10. 918, we need to read 9. And so you get the gist. So what are the conclusions here? The first thing that I want to say is that as someone that runs a storage service, you have a lot of power. You have a lot of power because you can talk to your customers, try to understand their use cases, and based on that, you can run some numbers, and you can come up with both a good replication strategy for your use case, and specifically if you're using Reed-Solomon encoding, you can actually come up with a good number for n and for k in order to guarantee your customers' expectations based on your expected failure rate. The other thing that is pretty important is catering to your use cases. So Reed-Solomon encoding is super awesome, but it doesn't solve every problem. There are actually some use cases where simple replication might be better. One thing that I'm thinking of is, for example, storing temporary data. So when you store temporary data, you might not want to incur that extra CPU overhead because that data is only going to stay around for, a couple of hours maybe. And finally, you don't need to stick to only one encoding. So in warm storage, for example, we have designed our system to support multiple encodings on the same cluster so that we don't need to have dedicated capacity for every type of encoding. Now, off to the second topic of this presentation, how we deal with downtime. So when we think about downtime, we think about specifically two different things. And by the way, here I'm not talking about service downtime, I'm talking about downtime at a host level. So we think about unplanned downtime, which is essentially usually when something breaks really bad and there's nothing we can do about it, it just goes away. And then we have scheduled maintenance, which is either when something breaks partially and then at some point we actually need to take a whole machine down to repair it, or just regular scheduled maintenance operations, like when we upgrade a kernel, for example, or we upgrade a firmware. So there is a whole spectrum of failure domains that goes from smaller hard drives to a bit larger servers, racks, rows, as in power rows, or power distribution units, data centers. For the purpose of this presentation, we're going to focus on everything from racks to smaller. So racks, servers, and hard drives. So let's see how we go about dealing with unplanned downtime first. The idea here is that we want to ensure that our data is available and durable in the face of failures. So how do we do this? Essentially two ways. So we try to be proactive, and we try to not put all of our eggs in the same basket, meaning that we try to spread our data across the failure domain. So we're not going to put all the encoded chunks for the same block on the same hard drive. We're not going to put all those chunks on the same server, or we're going to try not to put all those chunks on the same rack. The other thing, which is more reactive, is that we can do our math, and we can come up with a good reconstruction rate that allows us to meet our SLAs. So what's the reconstruction rate? Reconstruction rate is how aggressively we want to be in repairing data once we understand that something is broken. The pros of this approach, or the main pro, is that it works both for unplanned maintenance and planned maintenance, right? Because we don't need to deal with planned maintenance in any different way. This just works. There is a pretty big con to this approach, however, which is that reconstructing data has a pretty big overhead. So how do we go about this? Can we do any better? The answer again is yes. So this specifically relates to when we know that something is going to go down. So what we can do, very simply, is taking the data that we know is going to go away and copy it somewhere else, somewhere safe. In other words, draining. So the main pro with draining is that now we have faster planned maintenance operations. What does this mean? So we were sort of talking about a couple of slides ago about how we need to come up with a good reconstruction rate in order to meet our SLAs. That reconstruction rate is going to be based on what our customer needs are in terms of block availability and block durability, but it's also going to be based on the expected failure rate. Now, that means that if we don't do anything proactively, we need to slow down our planned maintenances to sort of match that expected failure rate that we did our computations with. In this case, there's no such constraint. So the thing that is essentially limiting the speed of our maintenance operations is just how fast we can drain. But still, we have the problem that draining comes with an overhead. For simple replication strategies, the overhead is essentially the same as repairing data. For read-solve encoding, it's actually smaller because in this case we don't actually need to repair data, so we don't have that read-repair amplification effect that we were talking about. The other thing that is not so great, I mean, it's pretty obvious, but this does not solve the unplanned maintenance use case, so it kind of means that now we have a more complex system because we need to deal with both things separately. My question again, can we do any better? Is there a better solution to this problem? So what we have done in worm storage is providing an interface that sort of looks like this. So we have a service, and we can ask this service, what hosts do I need to drain based on the list of machines that we want to take out of production at the same time, and based on the minimum redundancy that we want to guarantee for each of the blocks that are stored on those machines. And so based on those two things and the current state of the systems, what blocks are available, what nodes are down, the service is able to tell us, well, you need to drain nodes A, B, and C, but not any of the others. And so this is obviously more complex, and we have yet another moving part in our system. But the cool thing is that now it turns out we almost never need to drain, because we can almost always guarantee that every block that we have is not affected by our maintenance operations. But at the same time, we're not doing this blindly. So we know that when there's something that we need to drain, we can actually do it. And this also allows for faster planned maintenance operations because, again, we don't need to drain, so we don't need to take that amount of time that we need to copy the data somewhere else. So off to the conclusions of this part about dealing with downtime. The first thing that I want to say again is that also here you have a lot of power. Something that you need to know, especially for a team as my team that works for other teams. So we run a service, but we don't really own anything that relies on that service. We have other teams that need our service to provide some other service to someone else. And knowing your SLA basically means knowing the use cases of your customers and knowing what they need. This is important when we talk about draining because, for example, take a cold storage use case. So when you have something or someone uses you for cold storage of data, you probably don't need to be as aggressive with repairs. They can probably come back later. It's probably not a big deal for them, which is something that is like totally unacceptable for a hot storage use case. Because if you're serving pictures to your users, it's not cool to tell them, come back in 2 minutes and your data is going to be there. Another thing is knowing the availability of your unused resources. Because if you have unused resources, you can be a little bit more aggressive with repairs. At the same time, if you don't have unused resources in order to meet your SLAs, well, that's something you might have to budget for. Something that, based on your SLAs, you can go to your team that gives you hardware and you can say, hey guys, we actually need more hardware than you might think because we need to guarantee this better availability and reliability. And finally, another important dimension to this problem is the duration of the outage. So sometimes you know that a machine is only going away for 10 minutes because you're rebooting it to install a new kernel. And in that case, you probably don't want to drain because that's going to take hours or a day. In some other cases, you're swapping a hard drive. And well, at that point, you want to repair as aggressively as you can because you know that data is never, ever going to come back to you. So now off to the general conclusions. The first thing, as I mentioned, for a team that provides a service to other teams, it's really important to talk to your customers and to sort of understand what they need, both for your mental sanity, but also because that really affects the way that you configure and build your service for that. The other thing that is really cool is that Reed-Solomon is amazing. Reed-Solomon is so cool because compared to simple replication, you get both better availability and you also get better storage efficiency. However, it's not for free. You need to pay a CPU cost. You need to incur a read amplification effect, and so you also pay a network cost that comes with it. Now, I want to go back to my initial story about Josh. And I want to tell you what happened. So what we did in that case was that we were supposed to encode the data on that cluster using Reed-Solomon encoding, but we forgot to configure the encoding. So we were actually using type of replication. And the moral of the story, in a way, is that we could have prevented this if we had had better monitoring, which we didn't. And so I think kind of the global conclusion about this story is that there's no amount of cool technology that's going to save your ass if you don't have good monitoring. Because ultimately, your system is only as strong as its weakest part. So this is the end of my presentation. I think we might have a couple of minutes for questions. I'm not sure. I guess we have a minute.
So I'm curious about your capacity planning, because you said you were, running out, potentially going to run out of space before you got new hardware. Are you responsible for capacity planning, or do your users have to do their own capacity planning and pass that information on to you?
We rely on our users to do capacity planning for us. And that's because sometimes capacity planning is hard, and there's a lot of domain-specific information that you need to know. What new features they're coming up with, why are they going to store more stuff? Think about, for example, Facebook videos. That's like a lot of stuff that you need to store. And so obviously, you can't just easily infer the amount of storage that you're going to need in the future based on your past usage, but you actually need to rely on those teams to come up with some more sound numbers. So extrapolation is not necessarily always a good strategy with capacity planning.
Thank you.
Okay, I think I'm out of time. And if anyone wants to reach out for questions, I'm going to be around. Thank you.